In today's economy, cash flow is tight, and families are held captive to high interest rate credit card debt. Churchill Mortgage can restructure your current mortgage and significantly reduce these problems. Get a free analysis and learn how to eliminate credit card interest rates, lower bills, and start taking control of your budget. Get started at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLSconsumeraccess.org. Equal housing lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Go Ford for your next truck or SUV and find an easier way to buy with Woodhouse Ford today. And experience the convenience of buying with Woodhouse Ford. Lease a 2023 Ford Escape Active for $397 per month for 48 months and 7,500 miles per year. First payment and $299 doc fee due at signing. Security deposit waived. Tax title license extra with approved credit. Expires 12/04/2023.
This is SpaceTime Series 25, Episode 37, for broadcast on the 28th of March, 2022. Coming up on SpaceTime, parts of the Milky Way much older than expected, looking at the radio sky in technicolour, and the Australian Space Command commences operations. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Using data from the European Space Agency's Gaia mission, astronomers have shown that part of the Milky Way known as the thick disk actually began forming some 13 billion years ago. That's around 2 billion years earlier than previously thought, and just 800 million years after the Big Bang of creation. The findings, reported in the journal Nature, are based on positional data from Gaia's early Data Release 3 dataset, combined with measurements of the chemical composition and consequently the ages of 250,000 stars given by LAMOST, the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. The authors, who are from the Max Planck Institute, looked at stars known as subgiants. These are stars no longer on the main sequence, so they're no longer burning hydrogen into helium in their cores. Instead, these stars have started the process of shell burning, that is, converting helium to heavier elements in their core and burning a shell of hydrogen into helium around the outside of the core. Now, this subgiant phase is relatively brief in the evolutionary history of a star. It therefore permits the star's age to be determined with a great degree of accuracy. But it's still a tricky calculation. Under any circumstances, the age of a star is one of the most difficult parameters to determine. It can't be measured directly. Instead, it needs to be inferred by comparing a star's characteristics with computer models of stellar evolution. The compositional data then helps with this. It works like this. The universe was born 13.8 billion years ago with almost nothing but hydrogen and helium. Tiny trace amounts of lithium and beryllium, sure, but primarily it was a hydrogen and helium universe. 3/4 hydrogen, 1/4 helium. All the heavier elements, including the oxygen you breathe, the carbon you're composed of, and even the iron in your blood, was all made inside stars, either during their lives or when the stars died. These elements, which astronomers refer to as metals, were then incorporated into future generations of stars. So, stars which were formed early in the universe's history have fewer metals and therefore lower metallicity than stars which were formed more recently. And LAMOST provides data on this metallicity. And together the brightness and the metallicity allows astronomers to determine a star's age. Our galaxy, the Milky Way, is made of numerous different components. Now, broadly speaking, these can be split into the halo and the disk. The halo is the spherical region surrounding the disk and has traditionally been thought of as the oldest component of the galaxy. The disk, which is where the galaxy's spiral arms are located, is composed of two parts. There's a thin disk, and superimposed on that is a thick disk. The thin disk contains most of the stars that we can see in the night sky, and our Sun is a member of this thin disk. The thick disk is more than double the height of the thin disk, hence its name, but it has a smaller radius, and it contains only a few percent of the Milky Way stars in the solar neighbourhood. By identifying subgiant stars in these different regions, the study's authors were able to build a timeline of the Milky Way's formation. But what they found came as a real surprise. The stellar ages clearly revealed that the formation of the Milky Way fell into two very distinct phases. In the first phase, which started some 800 million years after the Big Bang, the thick disk began forming stars. The inner parts of the galactic halo may also have begun coming together around this time. But the process rapidly accelerated to completion about 2 million years later when a dwarf galaxy, which we call the Gaia sausage Enceladus, merged into the Milky Way. It filled the halo with stars. And as the new work shows, it also triggered the nascent thick disk to form the majority of its stars. The thin disk of stars, which includes our Sun, was formed later, during a subsequent second phase of galaxy formation, possibly when the Sagittarius dwarf galaxy slammed through the disk of the Milky Way on one of its earlier encounters with our galaxy. The analysis also shows that after the star-forming burst triggered by the merger with Gaia sausage Enceladus, the thick disk continued to form stars until the gas was mostly used up roughly 7 billion years ago. During this time, as stars were born and died and their content spread throughout the galaxy, the metallicity in the thick disk grew by a factor of 10. But remarkably, the authors see a very tight stellar age metallicity relationship. And this indicates that throughout this period, the gas forming the stars was well mixed right across the entire disk. And that suggested the Milky Way's disk regions must have been formed from very turbulent gas that was effectively spreading metals far and wide through the galaxy. The earlier formation of the thick disk points to a different picture of our galaxy's early history. Since the discovery of the ancient merger with Gaia sausage Enceladus in 2018, astronomers had already suspected that the Milky Way was there long before the halo formed, but they didn't have a clear picture as to what the galaxy looked like. The Gaia spacecraft will deliver its full third data release on June the 13th. This catalogue will include spectra and derived information like ages and metallicity. And that will allow astronomers to piece together the history of the Milky Way in even more unprecedented detail. This report from ESA TV.
Rotating slowly 1.5 million kilometres from Earth, Gaia is scanning the entire Milky Way. Since 2014, the mission has been mapping the distance, position and movement of 1.7 billion stars to reveal our galaxy as never before.
The scientific impact of the mission already is immense. We see 3-4 papers appearing per day. We're touching virtually every area of astrophysics, from very fundamental predictions of 50 years ago to new things that you see and the dynamics and the history of our own galaxy.
Capturing 70 measurements of every star, Gaia produces vast amounts of data. At a meeting in Groningen in the Netherlands, scientists have been discussing the challenge of processing and visualizing this information.
Gaia is probably one of humanity's greatest missions, one of the greatest catalogs of data that has currently existed for humans to go through. And it's almost impossible to give you all of the ways in which Gaia is impacting astrophysics.
Earthbound observatories provide a snapshot of celestial objects in the night sky. But by measuring how the stars are moving and visualizing that data, astrophysicists are using Gaia to trace the history and evolution of the galaxy. They've discovered, for instance, that stars born together in star-forming factories move in clusters or families throughout most of their lives.
It is mind-blowing. I can't believe we can do this. I could never have dreamed that we could pull away from our position on the Earth and actually see the structure of these kinds of associations. And then you can run time forward and see exactly how they're moving. You can compare and contrast how they're all moving differently. And I think it's a story of vast proportions in our understanding of how stars form and evolve.
Other science teams have used Gaia data to confirm today's Milky Way is formed from giant galactic mergers.
So most of the stars in the Milky Way rotate like the sun in a clockwise sense. So for example, what we discovered is a very large group of stars that are going the other way around. And so that's already very suspicious, and it tells you kind of that these stars were formed elsewhere, being such a large group. And it's also very old stars. So that was already the first hint that actually one component of the galaxy is probably made up from stars born somewhere else.
Across Europe, hundreds of people work on the Gaia mission, ensuring the data is accessible to everyone.
Gaia is currently in an extension of the original 5-year mission. What we do is we gather more data, we get better statistics, and then we can derive more precise results.
Galaxies come in all shapes and sizes, and while several 100 billion galaxies are estimated to be in our universe, only one of them is home to Earth. Our planet and its sun lies in one of the Milky Way's spiral arms, but while special to us, our sun is just one of around 100 billion other stars in the galaxy. So in order to better understand the Milky Way, its past and its future, the Gaia spacecraft has been surveying the skies since 2014, and it will make up to 70 observations on average for each star over the 5-year mission. The first data release in 2016 charted 1 billion stars, but only included the distance and motions for 2 million. The second release has now updated this to an extraordinary 1.7 billion, and with greater accuracy, including the distance and motions for nearly all the surveyed stars. We now know the position and brightness of 1.7 billion stars. Importantly, as well as the colour, we also know the distance and proper motion of 1.3 billion stars, plus the surface temperature of 161 million, the radius and luminosity of 77 million, and the radial velocity of 7 million stars.
The most eagerly awaited result from Gaia are so-called parallaxes, which is the measurement which gives a handle to the distance of the stars. And this is a very tough measurement to be done. And we have known since Hipparchus, the previous ESA mission, distances to about 100,000 stars. And Gaia is going to increase that number to above 1 billion. So that is a real revolution.
Obtaining the parallax measurement involved determining the apparent motion of the star by using 2 different vantage points along Earth's orbit around the Sun, and separating it from the star's true motion through the galaxy. Closer to home, Gaia observed 14,000 known solar system objects too, mainly asteroids, and far away it measured the positions of distant quasars to create a new cosmic reference system. But for astronomers across the world, the best is yet to come.
The essential thing of the Gaia mission is that the surprises will come later, because we make the catalogue, and it is the scientists in the community who are going to utilize it and give the scientific surprises to us.
Gaia is not only mapping the stars, it's giving us a new sense of our place in the universe.
And in that report from ESA TV, we heard from Gaia mission manager Fred Janssen from the European Space Agency, astrophysicist Jackie Feraghty from the American Museum of Natural History, astronomer Amina Helmut from the University of Groningen, and Gaia project scientist Timo Prusti from the European Space Agency. This is Space Time. Still to come, looking at the radio sky in technicolour, and the Australian Space Command formally commences operations. All that and more still to come on Space Time.
Right now, new and current customers can get any phone for free at US Cellular, so you can connect with all your family members this holiday season. You can even call your aunt who always makes you talk to your cousin, who's a dog. Or, maybe just send her a festive text. Get the gift of connection at US Cellular. Get any phone free today. US Cellular, built for us. Terms apply. Visit uscellular.com for details.
We value human connection with fewer distractions. US Cellular, built for us. Visit your US Cellular authorized agent, Cellular Advantage, located at 918 South Locust Street in Glenwood.
The Galactic and Extragalactic All-Sky Murchison Widefield Array, or GLEAM, is one of the biggest radio surveys of the sky ever assembled. The survey, which was published in the monthly notices of the Royal Astronomical Society, provides a stunning catalogue of some 300,000 galaxies visible from Australian skies. In its simplest terms, GLEAM is a large-scale, high-resolution survey of the radio sky observed at frequencies from 70 to 230 megahertz, observing radio waves that have been travelling through space, often for billions of years. The study's lead author, Dr. Natasha Hurley-Walker from Curtin University in the International Centre for Radio Astronomy Research, says the results show what the universe would look like if human eyes could see radio waves imaging the entire sky in technicolour. The human eye sees by comparing the brightness of three primary colours, red, green and blue. GLEAM views the sky in 20 primary colours. That's much better than the human eye can manage, and it even beats the very best in the animal kingdom, the mantis shrimp, which can see 12 different primary colours. Hurley-Walker and colleagues have been using the GLEAM data to discover what happens when clusters of galaxies, some of the largest objects in the universe, collide. The survey is also providing new information on the remnants of supernova explosions from some of the most ancient stars in the Milky Way galaxy. And it's even found the first and last gasps of supermassive black holes beyond our galaxy. The GLEAM survey is very much a key step on the path to developing the Giant Square Kilometre Array, or SKA project, which, once operational in a few years' time, will be the largest radio telescope on the planet. So big, it needs to be constructed over 2 continents. So, GLEAM is sort of providing astronomers with a glimpse of the universe which the SKA will eventually be probing. Hurley-Walker says by mapping the sky in GLEAM, scientists are helping to fine-tune the SKA's design and prepare for its even deeper observations into the more distant universe.
So GLEAM stands for the Galactic and Extragalactic All-Sky Murchison Widefield Array Survey, and it's a radio sky survey covering the low frequency range of the radio, and it covers all of the sky that's visible in Australia. That's about 30,000 square degrees.
What are you looking at?
So because it's in the radio, we're sensitive to high energy processes in the universe like synchrotron. So that is a process caused by electrons spiraling around magnetic fields, and they emit in the radio, so we can pick that up. Now, there's a lot of different objects in the universe that produce synchrotron, and the things that we've published most recently is a large catalogue of galaxies that are emitting in the radio. What's super cool about these galaxies is that they're located at really high distances. So we're talking millions to billions of light years away. And the reason they're emitting in the synchrotron is because they have supermassive black holes at their centres. And these black holes are accreting matter. The accretion disk has really powerful magnetic fields. And through processes where astronomers are still trying to understand, these magnetic fields can launch huge jets of plasma into space. And it's those that produce the synchrotron that we then see in the radio. So when we're seeing all of these galaxies at very high distances, we're actually getting a window into the physics at their very centres around these massive black holes.
And what's that teaching you so far?
So the really neat thing about GLEAM is that we observe over a really wide frequency band. So we can see both the lowest frequencies of the radio, like the FM band, where your normal radio works, and the kind of high frequencies around the digital TV. And because we observe across this wide band, we actually get a sense of the, in quotes, sort of radio colour of different objects. Now, that colour actually varies depending on the physics of what's going on. So one thing we can tell by looking at these radio galaxies is if they have a kind of blue radio colour, so they're brighter at the high frequencies and dimmer at the low frequencies, then we think that these objects are just starting out, so the jets have just formed, or possibly they're being confined by like a dense medium around them. Whereas if the jets are very bright at the low frequencies and dim at the high frequencies, i.e. they look kind of red to us, we think those jets are really old and the supermassive black hole stopped emitting jets a long time ago. So basically this is like a colour view of the universe that gives astronomers a direct insight into the physics of what's going on in distant galaxies.
Does it tell you anything about the mass of the very supermassive black holes you're looking at, or doesn't it work that way?
No, it not quite mass sensitive yet. There would be a lot of other calculations you'd have to do. But that's one thing that's nice about this survey. Because it's so wide, it covers the whole sky, it means that there's always other wavelengths that have been observed in any random patch of sky. So we can use lots of other radio surveys, we can use X-ray surveys, we can use all sorts of other information to pull out things like the masses of supermassive black holes. So I've just said what we can get directly for one specific class of objects, but a lot of the power of modern astronomy is pulling together observations from all different frequencies, and then that'll really help us understand the physics.
I take it GLEAM's the sort of thing that will eventually be included in the Square Kilometre Array project at the low end of the frequency.
Yeah, I guess that would be a wonderful ambition. I would love to be that person, in 20 years' time, leading the all-sky SK low survey. That would be pretty incredible. I mean, you'd be talking hundreds of times better resolution, incredible sensitivity, even wider bandwidth. I mean, you would just be seeing tens of millions of radio galaxies. That would be quite stunning. The data volumes would be difficult to deal with, and I don't think we even have.
No, that's always going to be a problem with the SKA, isn't it?
Yeah. So we'll see how that plays out in coming years.
As you've gone through the data and put this image together, are there any surprises that you've found, things that you've looked at and said, didn't expect that to be like that?
Well, I have a student looking for transient objects, so basically flares from stars or AGN or pulsars, things that might switch on in our survey and then be bright enough that even though we integrated a lot of time, we can still see them, and then they're not there in other surveys. And we found a really cool object. We were like, this is exciting. It's here one week and it's gone the next. And eventually we worked out that we'd rediscovered Jupiter.
Oh, right.
So it's actually quite bright at low frequencies. It's got this cyclotron emission. Anyway, it's cool, but unfortunately it's not a new discovery. People have known about Jupiter for a few years now, so...
I take it the emissions from Jupiter are coming when Io has eruptions, which are hitting the Jovian atmosphere and going through the huge magnetic fields between Jupiter and Io.
Quite possibly. So there's probably a project in there to look at all of the MWA observations of Jupiter, and then you could see, what's going on Io because of those. And I mean, that would just be another wonderful student project. We are basically swimming in data here. We have loads and loads of data, and we just need bright people to work on it. So anyway, the thing I would say about whether I found anything yet, I mean, I have found what do I call it? A distant radio galaxy that basically nobody had even thought was a radio galaxy. People thought this was just a normal galaxy with a quiescent black hole. But I was able to see that a long time ago, like billions of years ago, it had an outburst and had produced these really very large jets. But they were so old and so faint and so, only visible at the very lowest frequencies that I was the first person to find those. And that seems to be a whole class of objects which no one's really seen before because existing surveys don't have the sensitivity.
What sort of redshifts that at?
Oh, actually, this one isn't too far away. I think it's around 0.05, so it's a relatively nearby galaxy, which is why it's kind of astonishing, really, that nobody had known this before. So the jets actually are quite large on the sky, and just no one had the right sensitivity to pick them up.
We often talk about all galaxies having supermassive black holes at their centres. Is that what you're finding?
Yes, that's certainly consistent, but we don't know why some of them are active and some of them are not. And it's our data should help to solve that puzzle. Again, as I say, cross-matching with a lot of other catalogues and try and get a bit more of a window into the different environments that might cause supermassive black holes to switch on and off, and whether they have like a duty cycle, so whether they're on for some time, off for some time. All of these things are things we can help with our survey.
Doesn't that depend on whether or not they're feeding or not?
Yeah, so there are a really great complementary survey that will also help us answer these questions is the Australian Square Kilometre Array Pathfinder. That's at the same site as the Murchison Widefield Array, and they are going to do a hydrogen survey of lots of nearby galaxies, and basically that gets you a really accurate estimate of the masses of hydrogen in those galaxies, and then you can see whether that hydrogen is then turning into stars or whether it's feeding the supermassive black hole and so forth. So they'll have this tremendous hydrogen survey, and we have this tremendous, essentially, black hole jet survey, and so you can put those things together and see if you can understand what's causing this.
Try and watch clusters of galaxies colliding.
Yeah, so that's another thing. As you say, galaxies can form clusters. So if you have, you can have just isolated galaxies, but for instance, our galaxy is in a sort of smallish, it's not quite a cluster, it's more of a group of about 7 big galaxies and then quite a few satellite and dwarf galaxies. But the biggest groups are clusters, and they can have hundreds to thousands of member galaxies. And they have this hot X-ray gas in the middle of them, loads of dark matter. And when they collide during sort of structure formation of the universe, it's insane to even picture clusters of galaxies colliding, but they do. They form huge arcs of emission, again, in the radio because of the synchrotron emission. And we have doubled the number of detected these arcs from collisions that had ever been seen before. So we've doubled that number, and that's giving us a window into that structure formation. So like I say, this survey, the nice thing about surveys is you can just get so many different kinds of science from them. Yeah, I'm really hoping it's helpful for the astronomical community.
So this is really helpful for, say, understanding galaxy evolution and also, I guess, seeing the large-scale structure of the universe.
Yeah, so with those galaxies colliding, that's telling you about the history of structure formation. Potentially one could trace out the strands of the cosmic web. So if you've seen the millennial simulation, you have those wonderful filaments of dark matter. And it postulated that basically as those filaments kind of condense, the gas that's sort of floating through the universe is pulled into those local gravitational wells. And you'll see that at the node of every collection of filaments, there forms a galaxy cluster. But the idea is that the filaments are still there. They're just not quite as dense as the galaxy cluster. And so along those filaments, there'll be gas that's sort of falling inward. And the idea is that that gas can produce shock waves, which again produces synchrotron. I love this process. It's everywhere in the universe. And then we could actually detect that. And so we could see the strands of the cosmic web laid out in the radio. And of course, this measurement is extremely difficult, and the signal is expected to be very faint. But this is the right instrument to do it with.
We've been talking a lot about extragalactic all-sky surveys here. What about within the Milky Way itself?
So the Milky Way looks absolutely stunning in the GLEAM survey. It's really beautiful. A feature of the Murchison Widefield array is that it's sensitive to larger structures on the sky, unlike previous radio instruments, which could only see small structures. So we get this beautiful view of all the filaments of gas and synchrotron in the Milky Way. And we can also see supernova remnants. So these are the remains of exploded stars. And it's been this very long-standing puzzle to astronomers. We expect there to be a large number of supernova remnants based on measurements of supernova rates and also from the detected population of cosmic ray electrons. But there just don't seem to be enough remnants to explain the stats that we're seeing. And we think it's probably because they're just really, really faint and really, really large scale. And so GLEAM is just a perfect survey for finding these previously undetected supernova remnants. So that's something we're working on at the moment.
Are there areas of the Milky Way that we see very well with GLEAM? I'm thinking of maybe towards the galactic centre, Sagittarius A star.
The galactic centre is absolutely beautiful in GLEAM. It's really stunning. Obviously, the sheer density of material as you're looking towards the galactic centre means that to some degree you're only seeing the last surface from which things were emitted. But there's a very, very cool technique that I have a student working on, which can actually divide your view along the line of sight. So bear with me, it's a somewhat long explanation. There are massive stars in the galactic plane that produce a lot of UV radiation, and they completely ionize the hydrogen around them. And so they produce what we call H2 regions. So whenever we see one of these H2 regions, we know there's a very bright star in the middle. Now, a H2 region becomes opaque at the very lowest frequencies. So the whole galactic plane is emitting synchrotron radiation, but when the lower frequencies of that hit one of these H2 regions, they're blocked. So it's a little bit like if you have a stained glass window, that's got a blue panel or something. You're blocking everything except the blue light. So what that looks like to us in GLEAM, when it's blocking those low frequencies, is all of the red disappears from our image. So when we look at the galactic plane, we see mostly a glow of synchrotron, which is kind of orangey because it's bright at low frequencies. But then wherever there's a H2 region, it looks blue. And it's really bright. They're really obvious towards the galactic center. Now, the neat thing is that because these are at different distances, if you imagine the H2 region at some distance, between it and us is more kind of diffuse synchrotron stuff. So the further away you put that H2 region, the less blue it looks because there's more cosmic ray electrons and magnetic fields between us in order to produce normal synchrotron radiation. So if you combine mass estimates of the H2 regions, distance estimates of the H2 regions, and then the amount of flux and the colour that we see towards that H2 region, you can work out how many electrons there are between us and the H2 region and the very edge of the galaxy. So it's this complex model that you can produce of the galactic plane based on these radio observations.
That's Dr. Natasha Hurley-Walker from Curtin University and the International Centre for Radio Astronomy Research. This is Space Time. Still to come, the Australian Space Command commences operations, and later in the Science Report, a new study shows that Australia's black summer bushfires during 2019 and 2020 were so huge they actually changed the chemistry of the planet's stratosphere. All that and more still to come on Space Time.
The holidays start here at Baker's with a variety of options to celebrate traditions old and new. You could do a classic herb-roasted turkey or spice it up and make turkey tacos. Serve up a go-to shrimp cocktail or use Simple Truth wild-caught shrimp for your first Cajun risotto. Make creamy mac and cheese or a spinach artichoke fondue from our selection of Murray's cheese. No matter how you shop, Baker's has all the freshest ingredients to embrace all your holiday traditions. Baker's, fresh for everyone.
Australia's new Space Command has officially commenced operations. The command is the division within the Australian Air Force, focusing on supporting space domain awareness, sovereign control satellite communications and navigation, and space-based Earth observation and surveillance. It'll work alongside the Australian Space Agency, as well as research organisations and scientific institutions. Defence Space Command will include personnel from all three services, as well as public servants and industry contractors. In a speech to the Australian Air Force marking the new division's commencement, Defence Minister Peter Dutton says the new command's a necessary endeavour, especially in the wake of the ramp-up in hypersonic missile activity, anti-satellite missile testing, and other clandestine space operations now being undertaken by China and Russia.
Both Russia and China are already developing hypersonic missiles, which, as we know, can travel more than 6,000 kilometres per hour. All of us are watching the terrible conflict unfolding in the Ukraine at the hands of a despot hell-bent on reinstating Russia's imperial reach and spheres of influence. Australia is providing financial aid and military assistance to help Ukrainians defend themselves against their Russian aggressors. Our Air Force has successfully delivered military assistance on flights of C-17 Globemaster transport aircraft. Here in the Indo-Pacific, many nations have been subjected to different forms of Chinese government coercion over a sustained period, and we're witnessing China's rapid militarisation, the largest of its kind in peacetime and modern times. A build-up unaccompanied by transparency or strategic reassurance for concerned nations in the region and beyond.
Dutton says space will undoubtedly become a domain that takes on greater military significance during this century.
Space is becoming more congested and is already contested, particularly as the boundaries between competition and conflict become increasingly blurred through grey zone activities. Tellingly, more than 7,500 satellites orbit the Earth, with thousands more being launched each year. While space is primarily a civil domain to support navigation, communication networks, financial systems, scientific enterprises, weather forecasting and disaster response, it will undoubtedly become a domain which takes on greater military significance in this century. A domain which is now an operational theatre which provides space-based communication, intelligence and navigation to the joint force. We know that some countries are developing capabilities to threaten or degrade space networks, to target satellites and to destroy space systems. Countries that see space as a territory for their taking rather than one to be shared. In November last year, as part of an anti-satellite missile test, Russia destroyed its own redundant Cosmos 1408, which left behind a cloud of more than 1,500 pieces of lethal debris that will take decades to clear.
He also outlined initiatives to bolster space collaboration between Australia and the United States, including Washington's highly secretive National Reconnaissance Office. And he spoke of new joint Australian and US satellite activities.
Importantly, Australia and the United States are strengthening our alliance to support our mutual objectives in the space domain. The Australian Department of Defence and the US National Reconnaissance Office have committed to a broad range of cooperative satellite activities which will expand Australia's space knowledge and capabilities. Our partnership will also contribute to the US National Reconnaissance Office's pursuit of a more capable, integrated and resilient space architecture to support global coverage in a wide range of intelligence mission requirements.
Back in September, Australia, the United States and the United Kingdom announced the new Joint Defence Agreement, which will include the deployment of nuclear-powered submarines by Australia, as well as new missile systems, including new Harpoon and cruise missiles, as well as hypersonics.
One of our most promising joint ventures is that between RAF and Boeing on the air power teaming system, formerly known as the Loyal Wingman, but named officially yesterday as the MQ-28A Ghostbat. And he alluded to the capacity and capability of the Ghostbats and their brutal outcome. The uncrewed aircraft, with a range of more than 3,700 kilometres, is the first combat aircraft to be designed in Australia for more than half a century. It can fly solo missions or be teamed with crewed capabilities for force multiplier effects. The Ghostbat has already completed successful first missions. Compared to crewed capabilities, autonomous capabilities can be produced in quantity relatively quickly and inexpensively, with their loss or damage also being more tolerable. This is our vision for the Ghostbat, a platform which we anticipate will be of interest to many. In the Indo-Pacific, Australia is contributing to collective efforts to maintain stability and to deter aggression in this region. That's why we participate in exercises like Cope North in Guam, held in early February, along with the US Air Force and the Japan Air Self-Defence Force. Among our Air Force contingent, 11 F-35s were involved in the exercise, the first time our Joint Strike Fighters have participated in a trilateral exercise. Indeed, prior to Cope North, Australia accepted 4 new F-35s in Guam. Our Air Force is now operating 48 of a planned 72 Joint Strike Fighters, a 5th generation of multi-role aircraft, which is already or fast becoming a preferred fighter for many of our partners. Its capabilities are a critical part of our country's air combat system that includes, of course, the Wedgetail, the Growler and the Super Hornet. Another platform, which I'm sure will be a topic of discussion, is the P-8A Poseidon patrol aircraft. Australia has taken delivery of 12 of these aircraft, and last month the government announced plans to establish a new deep maintenance facility adjacent to RAF Base Edinburgh. We envisage that this facility will develop into a regional hub to service the Poseidons, but also other aircraft, like the Wedgetail, early warning and control aircraft. Our Poseidon aircraft already supports international efforts like Operation Argos, where we help enforce UN Security Council sanctions against North Korea in response to that nation's weapons program. And upon finishing a deployment for Operation Argos, a RAF P-8A Poseidon will fly to Japan to be part of a trilateral intelligence, surveillance and reconnaissance mission with the US Air Force and Japanese Air Self-Defence Force.
This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study has found that Australia's black summer bushfires were so huge they caused extreme changes to the chemistry of the entire planet's stratosphere. A report in the journal Science shows that smoke from the wildfires in 2019 and 2020 produced unexpected and extreme changes to stratospheric gases beyond any seen in the previous 15 years of measurements. Researchers using satellite data found increases in formaldehyde, chlorine nitrate, chlorine monoxide, and hypochlorous acid, as well as decreases in ozone, nitrogen dioxide, and hydrochloric acid. Scientists say these changes have the potential to affect ozone chemistry in unexpected ways. The research is the second paper in the space of a few weeks to warn about the potential impact of these fires on the planet's protective ozone layer. The Black Summer bushfires burnt out over 186,000 square kilometres of land, killing more than 3 billion terrestrial vertebrate animals, including many highly endangered species, some of whom were driven to extinction. The massive fires killed 34 people and destroyed more than 6,000 buildings. Smoke from the fires crossed the South Pacific Ocean, affecting New Zealand, Chile and Argentina. By the height of the fires in January 2020, NASA estimated that some 337 million tonnes of carbon dioxide and particulate matter had been emitted into the atmosphere, pervading the stratosphere and completely encircling the planet, and increasing stratospheric temperatures by between 1 and 2 degrees Celsius for at least 6 months. New research warns that artificial sweeteners may not be the healthy alternative to sugar people think. A report in the journal PLOS Medicine has found a possible association between consuming artificial sweeteners and an increased risk of cancer. Scientists analysed 24-hour dietary records and data from more than 100,000 French adults who also self-reported their medical history, socio-demographics, diet, health data and lifestyle. After adjusting for other factors such as age, physical activity, smoking and more, the authors found that participants consuming larger quantities of artificial sweeteners had a higher risk of overall cancer compared to non-consumers. Higher risks were observed for both breast cancer and for obesity-related cancers. While this study is observational and cannot therefore establish cause and effect, the authors say their findings do not support the use of sweeteners as safe alternatives for sugar in foods and drink. A new study has shown that limiting supermarket placement of seasonal candies and chocolates and increasing the availability of healthy alternatives may be enough to nudge people to purchase more healthy foods. The findings, reported in the journal PLOS Medicine, looked at grocery stores that removed freestanding promotional displays of Easter eggs and other candies in the 7 weeks leading up to last Easter, but still kept them available elsewhere in the store. The authors found those stores that retained their displays had an 18% seasonal increase in sales of those treats, while the display-free stores only saw a 5% jump in sales. And that translates to a difference of about 21 kilos of Easter chocolates and candy per week. In a second study, researchers evaluated 6 interventions to promote healthier products in 3 major UK grocery store chains, finding some interventions were linked to short-term changes in the healthier direction. A new study has once again reconfirmed what dozens upon dozens of other studies have already told us, namely that astrology is pure garbage. The research found no scientific proof that any of astrology is real, and there was a vast amount of data carefully explaining point by point why it's a load of trash. This latest paper focused on a critical examination of concepts and assumptions underlying the practices of the majority of astrologers in contemporary Western society. And just like every other scientific study, they found that astrology as typically practiced has no plausible non-paranormal explanation. It's all magic. Tim Mendham from Australian Skeptics says it's not even clear what a paranormal or supernatural explanation for astrology would look like.
Well, the final point is that on every level, on every aspect of it, you can look at astrology from any angle you like, and it does not hold. The arguments are poor. From the very fact that you start with physics and saying, what sort of impact do stars and planets, etc., have on us to influence our character and our future, etc., leaving aside sun signs for the time being, which are obviously broad brush approaches. Any gravitational effect or any sort of effect from stars and planets is less than negligible. I mean, you have to say, the doctor standing beside you when you're born, he would have more gravitational effect. A chair in the room would have more gravitational effect than a star or a constellation or a planet. From a physics point of view, it's wrong. From an impact point of view, if you look at the results, it doesn't hold up at all. They're trying to sort of suggest that someone's future is decided by astrology, the star signs, when you're born, as opposed to when you were conceived. I would have thought conceived to be better, but people can't pin down when you were conceived. That's a bit harder to do a star chart. But when you were born, is that under certain constellations and planets and things, those specific characteristics of those constellations and planets will impact you and your character, etc. The trouble is different cultures have different characteristics of planets, etc. I think as with this one particular article, this paper critiquing astrology says that while in ancient Greek philosophy, Mars was the god of war, in Aztec philosophy, the sun was the god of war. So there are differences like that. Of course, apart from the very nature that constellations are an artifact.
Yeah, the constellations
that we
don't
make
line up anymore.
Yeah, and that in
And
Babylonian...
there are more of them than there should be.
No, but there's constellations all over the place, all over the entire sky, as you know, right? As your listeners would know, it's not just the ones on the ecliptic, right? Which is the ones that we quote in astrology, the 12 zodiacs
Yeah,
around
there
there.
are 13 on the ecliptic.
There's 13. There's Ophiuchus, which is conveniently ignored because you try dividing 13 into trines or quads or whatever.
Sizes.
Well, absolutely. They're not all sort of 28 days or something like that. One of them was very long, 30-odd days, and one of them was about 8 days. So, I mean, you ignore that. That's another angle you look at. The constellations, which actually don't exist in reality, right? Because one star's way back there and one star's up here, and it's only the angle you're looking at it from. The fact that they're only in the sky for totally different periods of time, and that there's another one that they don't count because it's too hard to make calculations based on 13. There's no gravitational impact at all, and that the cultural aspects of it, when they were created, these star signs and that sort of stuff, changes depending on where you are, and that the whole process ignores the precession of the equinox, which moves the sky around every whatever. And, we don't start with Aries these days, we start with Aquarius. And so you're not an Aries, you're an Aquarian, or vice versa. I forget which way around it goes. And it doesn't work apart from that. Apart from being pretty pictures, it has no basis in anything at all. So it's one of those areas where I think science can actually say 100% wrong. Most areas you can't say 100%, right? You can say, a possibility, but in this case, I think it's pretty safe to say 100% wrong. And this paper looks at it from a cultural, from a scientific, all sorts of point of view, but mainly from a cultural point of view, and says that, no, doesn't work. It's different depending on where you are. So treat it as fun only.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.